you should see that on your dashboard, on the Zoom
Oh, I see.
dashboard.
It's in more.
Yeah. Okay. Yeah. If you're not full screen,
And
I'm
can they do polls and quizzes?
yeah, you can do polls and quizzes. You should be able to create those.
Can I create them or can David create them or just me?
No, both of you should be able to.
Okay, David, I'll ask you to create some of this.
Sorry, my audio cut out. What do you need me to create?
When we have polls and quizzes, I'll ask you to create the polls and quizzes since we um since we were planning to have breakout rooms, we did not realize it was a webinar. And so I think we're just going to modify on the spot, which we're good
Okay,
at.
I'll start making them now.
Yeah, okay.
Or
I'll,
or
I'll,
when you tell me.
yeah, I think that'll be more effective.
Okay. I'll play with it
Um,
right now though.
and what's a good time to start?
Let's give it another couple of minutes and then I'll have you get started.
Okay, great.
Real quick, how do I make the poll question? I see a bunch of poll questions, but I don't have an option to make one.
Yeah, so at the top right hand, there should be a plus button.
I don't see a plus
I just see
button.
search all types, and at the top I see all and starred.
Okay, let me make you host and then that might. Okay, David, you're host now. Does it allow you now?
Let me refresh this. I don't see a plus button anywhere.
Oh no.
I see a list of poll questions, but
Somebody
not
else
when.
pulled this off, is what we can see, because
Yeah,
these questions are.
Yeah,
Um,
it lists the ones from before as well. If you don't mind just shooting me an email with what you need made and I can make them on the back end.
okay, David, you're going to be in charge of all of this.
okay. All right.
Whatever, you're earning whatever
I
you're
got it. I
getting.
got it. I
What
got
are
it.
you
I'm good.
getting?
Oh no, I got it. I'll make the questions.
I'm not worried.
Okay, cool.
Actually, okay, so to those of you who are listening to this enchanting conversation about using Zoom, my apologies. This is probably the millionth conversation that you've now heard in your lives about using Zoom. My name's Dana Friedman, and I'm going to be teaching this class, which will be a special topics class on molecules for quantum networks. We assumed absolutely no background whatsoever, and we're going to dive into this from a very, very, very fundamental level. If this is boring for you, if you're a chemistry grad student, etc., I might recommend fleeing at this point, but this should be a fun class. We'll start in another minute or two. And in the meantime, I'd love it if David, who's my co-teacher, could show his face so that we can just all meet him. David is a grad student in my lab, and I see that he is physically sitting in the lab, and so talking um, might be more of a challenge than anticipated.
Should be fine.
Okay. Um, okay, great. So we're gonna give this one more minute and then we'll start. Actually, David, can you make a first poll question about background?
Yes.
Thanks. Okay, so this seems like a reasonable point to begin. We're going to be talking about how molecules interface with quantum networks and the opportunities for molecular design. And you might have noticed that this is probably the only course in the entire quantum winter school that requires absolutely no background. And the goal of this course is to connect molecules to the quantum network and encourage you to think about building up components of a quantum network from the basic building blocks of matter, which are atoms that we can move into different units. Molecules can be created through chemical synthesis. They can also be created using the same strategies as cold atoms, using, for example, optical tweezers to create bimetallic species. And so we're going to build up some of the basic concepts of, well, molecules and where molecules fit into the quantum network. So, why molecules? What can molecules do? And so if David is ready, what I'd like to start with is actually a brief quiz of everyone's background. Um, and I'd like to see where we're coming in so that we can make some modifications to how we present today's material. David, do you have a poll?
I just emailed it to Brian, so she should have it in a
Okay.
second.
How about you tell me when it's ready and I'll just keep talking. Okay, good. So we're also making some modifications to the class structure because we were planning some breakout rooms, but we're just going to do all of the things we were going to do in breakout rooms in the larger group because of the webinar, not Zoom format. But this will be a highly interactive class. So what's the role of molecules in the quantum internet? In a very simplistic way, molecules expand our design platform. Molecules give us control over a lot of different parameters. The quantum internet is very far from monolithic. It contains all sorts of different components that you've heard about extensively in the other classes in this school. And I'm not going to retread any of that ground. Um, we're going to begin by talking about the role of molecules in the quantum internet. How do we build a molecule from first principles? What's a molecular orbital? And here we're going to begin with dihydrogen, which from a chemistry perspective is the simplest molecule that we have. We'll complicate this further with d orbitals as we move out to metals, and then we'll extend it to f orbitals. And in each of those areas, we'll talk about the systems that we're building and their potential role in a quantum internet. So just to begin with a quick reminder, with a quantum internet, we have a network design. In the network, we have individual nodes, we have non-local entanglement, and we have spin photon entanglement. And each of these requires different parameters. One thing that you've probably heard about in the previous classes is how unique a quantum repeater is, how there are very special components for the quantum internet that don't exist in the classical internet. To create every one of these components, we need to think about materials and their design properties. Molecules are one class of material, but a lot of the systems that we're showing can be translated seamlessly from molecules to materials. And so in order to make a bit of a case for molecules, I'm going to go back and step aside into a foreign field, which is quantum computing. Here, I wish I could do a quick poll. I can't make a poll either. Okay. I would love
We
to
have the
ask.
first poll.
Okay, let's start with the first poll. David, can you launch that?
Yeah, give me a second.
Yeah, we'll see.
Okay, great. So super helpful for helping us think about And also, if you have zero chemistry experience whatsoever or a high school chemistry class, then just check the first option. That's equivalently helpful. Um, oh, I wish I could make polls here. Okay. Okay, great. So I'm going to end the poll. This is very helpful. And we're going to go to a more physics system briefly. So this molecule right here is one of the first quantum computers that was ever created. And this is something that we as chemists love. Physicists chose this molecule or chose a molecule in general because molecules offer atomic precision, control, and reproducibility. And those are three attributes that we need for components in a quantum network. We can easily place every atom exactly where we want, and we can design and modify its electronic properties. The ability to design and modify these electronic properties is incredibly powerful for creating new systems. But to do that, we have to think about our design properties, what we want to put in a particular place, and how we want to modify it. When we're thinking about a quantum network, one of the key parameters that we're thinking about is emission and integration with optical cables. We're thinking about entanglement. We're thinking about frequency, and we're thinking about quantum control. And so in each of these areas, we can think about what type of a system we want and how we can build it from the ground up. In this system right here, this is a molecule which does not have a spin optical interface. That is to say, it does not have a way to interface control of its magnetic sublevels with an optical excitation. This system was controlled entirely by, well, radio waves in an NMR experiment, in a nuclear magnetic resonance spectroscopy experiment in an instrument such as the one shown here. So an NMR experiment can be used to simply implement Shor's algorithm and factor the number 15 into its constituent factors. So that's something that is really exciting from a quantum perspective. Not NMR-based quantum computing, but the ability to precisely design the structure and function of your qubits and their spatial precision. So, moving away from this NMR example, how do we go back to the beginning and think about building a system with the right parameters? And to do that, we have to really go back to general chemistry. In a molecule, we can control both our nuclear spins and our electronic spins, and we can also couple them together into larger systems. If we want to create something which is suitable for a quantum internet, we need to think about creating a spin optical interface of some kind. And so a spin optical interface is analogous to systems that you possibly have seen earlier in classes in the prior in the beginning of the week, where, for example, you have, and I'll bring this out again, an anionic nitrogen vacancy, pair defect in diamond, or a tin vacancy, or other similar centers that feature this optical readout of spin information, or a connection between an optical photon and a spin photon, where you have the two components that really make this nice relay between a simple flying qubit, a photon that can transmit your information, and the spin, which can be much more easily manipulated. So we can do this with molecules in general, design out a spin optical interface, but this slide right here definitely does not presume no chemistry knowledge. So let's build up the chemistry knowledge so we can think about how we would take a system and ab initio design a spin optical interface. And that's something that we can apply to molecules, but we can also apply it to solid state defects. Over the past 10 years, there have been a plethora of both proposed and designed defects. For example, defects in silicon carbide. There's recently an intriguing proposal of long coherence times and bismuth defects in manganese oxide or magnesium oxide and calcium oxide. And so in all of these systems, we're using similar chemical principles. And so while we're talking about molecules here, because molecules are offer a lot of synthetic tunability, we can also think about these attributes in solid state materials, such as the ones that you heard about earlier this week. So let's start from the perspective of a diamond. Now, actually, David, can you make me a question that says, have you seen this? Yes, no, maybe. And we're just going to keep reusing that poll.
I actually enabled the chat. So if people want to drop yes, no, maybe in the chat, I think we can do that now.
Oh, great. Everyone. Okay, so we can't have this as interactive as I hoped, but can you all tell me, are you familiar with the anionic nitrogen vacancy pair defect in diamond? Some feedback. Okay. Okay, this is awesome. Okay, so I'm going to introduce this. This is so helpful. Y'all are the best. I taught Gen Chem April 2020, first class of the pandemic, and I got used to the format of Zoom with an audience that's a little hesitant. So I'll keep asking you for feedback. Okay, so right here, we have a diamond. And that diamond is a carbon lattice shown here. A carbon lattice is a fairly stable allotrope of carbon. Of course, diamond is, I love the heart. Diamond is metastable, graphite is forever, but diamond has a significant metastability, so it persists for a long time. If we want to put a defect into diamond, there are some defects that grow naturally. The anionic nitrogen vacancy center is one of the defects that grows naturally in diamond, but we don't want to rely on naturally grown defects in diamond. For all the reasons that you can think of, that mining something and then using it is not the best way to get a pure material. And so in general, if we want to put defects in a material, we take a diamond, and we don't do this. There are very few people that make defects in diamond. One of them is Element 6, which is a company that I believe is owned by De Beers. And more recently, there have been some efforts through different governments, for example, the US government, to create foundries to place defects in diamond. For many reasons, but because it's probably good to have our own way of placing defects in diamond that doesn't rely on De Beers. But okay, so take a diamond and you bombard it with ions. And when you bombard it with ions, you create a scatter shot of defects. One of those defects that you can get through bombarding with nitrogen ions is schematically shown here, where we have a nitrogen atom that's replaced one carbon atom and a vacancy that's replaced another atom. The one that we're talking about is anionic, which means that the overall charge of this system is -1. And so we have the anionic nitrogen vacancy pair defect in diamond. This defect is really cool because for many reasons, uh, but effectively, what you have, for those of you that have taken some organic chemistry, you effectively have a pentavalent carbon. The anionic charge is traditionally depicted on the vacancy center. So here we have the anion bound to, or the vacancy bound to 3 carbons, and then it necessarily must have 2 additional orbitals so that you can have a spin of 1 comprised of the 2 unpaired electrons. So as you can imagine, this is not a very stable species. And so it can only be created through this highly kinetic approach of shooting ions at this diamond. And so these systems are great, as are analogous defects in materials, broadly speaking, that have been used as some of these emitters for quantum networks and other applications such as quantum sensors. So these defects are really powerful, but they lack any adjustable parameter because of the way they're synthesized. And so from a top line, as they relate to quantum networks, you can't tune these towards fiber optic cables. So fiber optic cables are most transparent around 1550 nanometers. And so you can't rationally design your system to emit in that region, which is one challenge. And so you're facing a lot of loss through fiber optic cables. it's also very difficult to position these things spatially where you want them. So for example, let's say that what you want is to, for example, use this as your spin optical interface and then have a close in proximity nuclear spin. So nuclear spins are really good at being this evocatively named quantum memory, which is something that you might have heard about earlier this week, but a system where you can store information because nuclear spins are smaller and they're more protected from the environment. And so if you want to embed and integrate a quantum memory locally, it's very hard to get your C13 right next to your NV center. And you have to, the poor grad students that work with these systems take them and they actually index them by hand and look for just the perfect system. And then once they have it, they hold it in place. And so these are really great and powerful things, but you can imagine by expanding our catalog of materials and molecules, we can get closer to things that have exactly the right parameters. So, oh, thank you. This is great, David. Thanks for answering the question. So there was a great question that I just saw in the chat. Thank you so much for asking questions in the chat. This is wonderful. So let's think about this. So this is unstable, but when we think about organic chemistry, we can think about something that's a thermodynamic product or a kinetic product. We can think that there are two things and there might be something that has the minimum stability, but that might not be how something is formed. So let's say that it's so much more likely for these two things to crash into each other like this, and then they crash. Once they're formed, if they're in a local minimum, it can persist even if it's not the most stable configuration. And so this, we have to think about what would cause it to dissipate. And so let's say that this system that's relatively unstable kinetically were to dissipate. How would that happen? Well, if we wanted to move it over, we'd have to break a carbon-carbon bond and we'd get exactly the same thing. So there would be no thermodynamic driving force. So if we got really close to the surface, then suddenly we would have a thermodynamic driving force and this would be possible. But in the absence of that, the um, the product of the reaction would be no more stable than the reactant. And so it has this inherent kinetic stability once implanted in the diamond. This is a great question. And thinking about all of these pathways is, in my opinion, a large part of the importance of chemistry in the quantum picture, because everything is a material, right? Everything we use in some form or another is comprised of atoms that have been placed where we want for a specific electronic property. Okay. Let's continue. That was a great question. And David, thanks for grabbing the chat questions too. I thought, okay, I did not animate this correctly, so we will just do this. Okay, so if we want to think about how to create these things, let's step way back to the beginning and let's step back to how we construct molecular orbitals. Let me just ask in the chat, are we all comfortable constructing a molecular orbital for dihydrogen? If not, let me know and we'll go through it quickly. Okay, awesome. Okay, so, oops. Okay. So we have dihydrogen, we take our atomic orbitals. This is a collection of some atomic orbitals that we like to think about. Our s orbitals, our p orbitals, our d orbitals. David made this slide. Love these images. And David's also done a good job putting some radial nodes in here. And the d orbitals we'll return to, but I just want to highlight that of course, we go from our 1s orbital to our 3p orbitals to our 5d orbitals because that's the way our quantum numbers go. And when we have our hydrogen atom, we take our two atomic orbitals, we mix them, we get our bonding and our anti-bonding levels, and then we have our two paired electrons. So before I go to the next slide, why don't you just take a minute and see if you can remember why H2 is stable, but helium is unstable. He2, I mean, not atomic helium. Okay, so I see its s orbital is full of electrons, and that's true. But let's say that the way, and David's diagram here gives away the answer a little bit. But let's see if I can annotate. Okay, let's say we add an electron here, and we add an electron here. If this separation was equivalent in energy to this separation, would you have any He2? What do you think? I think you would. I think that if you have an, oops, let me clear that. I think if you have an equilibrium between two equal energy levels, uh, I think if you have two energy levels that are equal, then you have a thermodynamic equilibrium between them. So if you have two possibilities that are energetically equivalent, then I think both of them will form, right? Because if the top energy level and the bottom energy level are equal, the stabilization is equal to the destabilization, then some percent of the molecules will form. So I think that we're so well trained that the anti-bonding is more destabilized than the bonding is stabilized, which is correct, that we forget what would happen if the energy levels were equivalent. If the energy levels were equivalent, then what that would mean would be the stabilizing interaction would be precisely, which is this bonding combination, would be precisely equal to the destabilizing interaction. And when you have two competing forces that are equal, then your thermodynamic driving force would be zero, which puts you into an equilibrium state where both sides of the equilibrium are represented. Does this make sense to everyone? Okay, thanks. Great. Okay, so we're going to move on to the next slide, which is why is He2 unstable? And so this is exactly the reason. It's because the bonding interaction is less stabilized than the anti-bonding interaction is destabilized. So with this, and because we're all comfortable understanding what a molecular orbital is, I'm going to ask you to work on a problem on your own, and that is dioxygen. So I'm going to ask you to, on your own, because we don't have a breakout room, but ask David for help. Let's work on the molecular orbital diagram for dioxygen, and we're going to spend a good 4 minutes on this. And the question that I want you to answer is, and remember, this isn't for credit. No one cares if you get the right answer, so don't look it up. What is the spin state of dioxygen? And I know some percent of you know the answer, but let's just draw out the molecular orbital diagram of dioxygen, which is O2. And I'm going to stop talking and you can put any questions in the chat. And I'm just going to check my time on my phone. And we're literally going to give you 3 to 4 minutes on this right now.
Any questions in the chat, I will answer with my voice.
Okay, let me check in. How are you all doing? Do you have the answer or do you want more time? All right, I see one answer. Nice job. Does anyone want another minute or so before we move forward? Because being able to draw this is kind of the core of what you need to start thinking about drawing more complicated molecular orbital diagrams. Nice job. Okay, let's move to our actual diagram. And so what we have here, so we have our oxygen 2p orbitals, and we generally assign the bonding axis as the z-axis. And so we have our 2pz forms our sigma orbitals, and what we can see with our molecular orbital picture is our pi orbitals indeed have two unpaired electrons. And this is one of the clearest examples of why building up from molecular orbitals is necessary to understand basic chemistry. And so what we've done is we took one atom, we put it on one side, another atom, put it on the other side, and built from our atomic orbitals to our molecular orbitals. And when we do that, that's very straightforward for a diatomic molecule. And this is something that you can use for a molecule like O2, or if you're a person that, for example, works with cold atoms, you would use a very similar approach to construct the molecular orbital diagram for example, a dipotassium molecule that can be kept at ultra low temperature. Um, oh, huh. Aw, David. Um, okay, so um, yeah, we can see that this is also something that enables us, even at the simplest level, to design systems. So if we want to say, how do we put together a diatomic molecule that has unpaired spins? We would think about it in this way. And so what are we thinking about here? Well, the way that we have our unpaired spins is we have two energy levels that are degenerate, that are the same level, which enables us to have unpaired spins, and we don't get spin pairing. It's this very concept that enables us to design both lanthanide and transition metal systems that are operable for use in quantum networks and other systems. And in fact, that's very similar to the way that you could think about the electronic structure of the anionic nitrogen vacancy pair defect being designed. In that system, we similarly needed two, you can think about them as molecular orbitals. In a magnetically dilute system, you can draw a molecular analog. And so there you can think about creating a molecular orbital where you have two levels that are sufficiently close in energy that the electrons won't pair. Dioxygen is a great example of this, but we can extend it to every other system. We can think about this for, well, for any solid state material or for any molecule. And so let's remember that here we had this criterion of having our degenerate levels so we didn't get electron pairing. And that drove our S=1 system formation, which is actually something relatively hard to design ab initio. If we want to move from a diatomic system to a triatomic system, or of course beyond that, which is where we're going, it becomes prohibitively complicated to have each individual atom have their own home. So instead of having one one atom on one side and one atom on another, instead what we do, and I'm just seeing this diagram's actually backwards of what we usually do, but we choose one atom that's the central atom, and then we take the other atoms and reconfigure them as an entire set. So what we can think is, let me see if I can annotate this out. If we have, for example, and I'm going to show this later, a metal, we can put it here, and then we can put ligands or things bound to a metal over on the other side. And in the middle, we would have our molecular orbital diagram. And so if we create something like that, what we would do is we'd have all of our atomic orbitals for our metals here. And then the ligand set, we would design it based on symmetry. And so here we see an example of this with water. And so with water, we have H2O, which of course has an angle to it, but we're going to ignore that for my stylized drawings. So we have the atomic orbitals of the oxygen is our centerpiece, and they're shown here. And then what we want to do is we want to mix this with the atomic orbitals of the hydrogen. Because we can't, because we don't really think or draw in 3 dimensions, we're going to collect the hydrogens into a set of, if it's done correctly, are referred to as symmetry adapted linear combinations. Can I just ask quickly if anyone has seen symmetry adapted linear combinations of orbitals before? Okay, awesome. Thanks. This is really helpful. Okay, so I'm going to erase everything on the screen so I can close the chat. Okay. Um, so these right here are symmetry adapted linear combinations. The way that we get our symmetry adapted linear combinations is we take the aggregate of the thing that isn't our central atom, and we come up with different ways we can put it together. I'll briefly touch on this later in the class, but in the most formal setting of that, this can be derived using group theory, where we look at all of the different ways that these sets are mathematically allowed to transform. And I'll show you one chart later of what the group theory analysis would give you. But in this case, we're going to do the hand-wavy equivalent that for the cases we're looking at will give us a very similar answer. If you're interested in digging into the proper group theory approach, David can also throw some really good references into the chat. David, like ABW and Cotton, and I mean, like, obviously Figgis. Um, okay, so we have our sets of orbitals that we want to think about. So here we have, and because we have 2 hydrogen atoms, atomic orbitals, so we have 2 1s orbitals that we're putting together, and when we put 2, we always get the same number of orbitals out that we put in. So we have 2 hydrogen orbitals in, we're going to get 2 salx out. And so we can actually see if this is our structural configuration, there are really only 2 things we can do, right? They're in phase or they're in out of phase. That's it. And so we take those fairly intuitive combinations that we can build up and we combine them with the atomic orbitals. And so what you can see here is you take your atomic orbitals and you mix them with your symmetry adapted linear combinations, and you can see that you have configurations that have, for example, here, a lot of bonding character. So you can see how here we have extensive overlap between those orbitals, and here we have extensive overlap between those orbitals, and there are no nodes in the bonding axis. And because there are no nodes in the bonding axis, we know that this is a sigma orbital. And so we also have configurations that are non-bonding. And we have a configuration like this, which is the anti-bonding equivalent of this orbital. And so for every bonding combination, we have a corresponding anti-bonding combination. And so this is exactly like the O2 diagram that you built up so well. Except it involves using, instead of 1 atom, 2 atoms. Okay, so hopefully, maybe let's just take 30 seconds to see if there are any questions. Okay, we'll move forward. So this is the diagram that we get from what I've just described as in some ways a fairly hand-wavy approach. Now, the thing that's kind of cool about this is if we have an electronic structure.
Dana, we have a question.
Oh, thanks, David. Great question. How do we identify the central atom when the system has a large number of atoms? So if we're thinking, so that's a great question. There are a few answers to that. If there's one atom that's different than the others, then that's where we want to start. So for example, if you have a metal surrounded by organic moieties, you start with the thing that's different. If you have, for example, a large organic molecule, if you're looking at like aspirin, then you can't use this approach. You have to use a different approach to build up the electronic structure. And so an approach like this will work best if you can identify your central atom. And so if you can take your molecule and you can figure out the basic symmetry of it using something as the center, this will be most successful for molecules where you have some symmetry elements to it. And so if you have some symmetry elements, then you're more likely to be able to come up with the answer. That's a great question. So for a molecule like aspirin, you just have to weigh all your orbitals together. And there is no way to develop a symmetry adapted linear combination of your orbitals. And aspirin, David, does aspirin have any symmetry elements? It doesn't, right? Okay. So anyway, that's a great question.
Not
If
easily identifiable ones.
that's what I thought, but
It's gonna have a mirror plane, but yeah.
oh, it has a mirror plane? Okay, we will move on.
The Lewis structure does, whether or not the
Oh,
crystal
yeah.
structure does, I'm not sure.
Yeah, okay. Um, okay, so does that answer your question? That something that would be the center of a symmetry element means that you can probably work with this and identify the molecule, but if it doesn't have um, something which is either different or would be the center symmetry element, then it's more difficult, and you probably would need a different approach where you would connect all of your orbitals together, likely computationally. Okay, so when we're developing a molecular orbital diagram of any kind, one super reasonable question is, how do you know? We're just asserting things left and right. And so with dioxygen, how do we know is super easy. Dioxygen's paramagnetic. You take oxygen, you dump it on a magnet, and you see that it responds to a magnetic field. That's a pretty good indication that it's paramagnetic. With water, how do we know that these are the particular energy levels? And the way that we know is we can take a photoelectron spectrum. We can basically eject electrons out of the molecular orbitals and see their character. And we can see what all those levels look like. And so we can see here the photoelectron spectrum of water, which matches the molecular orbital diagram of water, which is a really powerful way to see that this approach is correct because we can match it directly to the experiment. Okay, so this is a broad outline of the way we build up these systems. If we want to move from something like water to transition metal or lanthanide complexes, we have this beautiful menu of different options. And so when we're thinking about states that have, for example, a spin optical interface, which is the goal of developing systems that can be part of a quantum internet, you probably need some sort of spin optical interface. There are other strategies like all photon-based systems, but for a spin optical interface, you probably want to pick from something where you can control your spin states. And the things that have been used for control of spin states are largely transition metal compounds, some main group elements. For example, here's tin, um, which is used in some defect systems. You also have down here the lanthanide series, and erbium right here has been extensively discussed for quantum communications applications because erbium emits nearly perfectly into the telecom band, into the point where there's the lowest loss in a fiber optic cable. And so erbium emits naturally at approximately 1550. And that's a really nice advantage. So for the remainder of this class, we're going to go through how we think about building up transition metal systems and lanthanide systems and how we control their energy levels, and we can just make choices. And with this knowledge, you can basically on a pen and paper with pen and paper say, this is the type of system that I want to make, or this is the type of system even that I want to buy, or why hasn't anyone investigated this type of system? And so it's something, in my opinion, really exciting for looking at quantum communications overall. Okay, so we love the periodic table as chemists. To us, this is absolutely home. And when I teach here at MIT, all of the students that I teach are required to memorize the periodic table, which is more fun for me than for them. But this is our home. In this class, you will not be required to memorize the periodic table. But the features worth noting, just in case the language isn't as familiar, the transition metal series here is where we're filling d electrons. The lanthanides are where we're filling the 4f electrons. Actinides are where we're filling in the 5f electrons. Here, this is called the main group. Um, and sometimes this is called part of the main group, and sometimes they're called the alkali and alkaline earth metals, um, depending. One last distinction, which you'll frequently hear in discussions of quantum networks, because a lot of quantum networks use lanthanides. The aggregate of the lanthanides, actinides, and these metals here are referred to as the rare earth metals, which is, as you probably know, a misnomer, and they are not necessarily rare. Uh, for example, uh, well, this is cheating, but ruthenium is far more rare than any rare earth metal that exists naturally, not nobelium. Okay, so if we want to think about building these complexes, we want to think about what will work. So metals, when they bond to things, tend to fall into a number of different geometries. This is a bit circular because part of the reason they fall into these geometries is these are good configurations for their d orbitals. And so much like by bringing the two oxygen atoms together, we constructed a manifold of molecular orbitals that included bonding, non-bonding, and anti-bonding orbitals. When we bring a metal together with a ligand field, we construct a manifold of molecular orbitals. And effectively, we tell the d orbitals where to go. And that's the key attribute of working with metals. So here are some configurations that we're going to revisit. Octahedral, trigonal bipyramidal, tetrahedral, square planar. And we're reordering our d orbitals, which tends to be where our electrons are. And so the energy levels below the d orbitals are traditionally referred to as the core orbitals of the molecule, and they're almost always fully filled. And so the electronic properties that we get from a molecule reside largely in the d orbitals. And so um, I think you're probably all familiar with the d orbitals. So we'll just go through these quickly. We have the three orbitals that are off axis here, the XY, XZ, and YZ orbitals. And then we have this on axis orbital, the x squared minus y squared, and the d squared orbital, dz squared orbital. One really simple way we can think about constructing molecules and telling the d orbitals where to go is something that I'm now going to give you as a problem, which is to use an approach called crystal field splitting, where effectively what you do is you draw out, let's see if I can do this. You draw out a coordinate system, you put each of your d orbitals into it, and let's say that you're using an octahedral ligand field. You assign a charge at each point, and you see how much overlap there is with that charge. So let's practice on these two orbitals right here. So why don't you take a minute and see how much overlap you have with an octahedral ligand field of the x squared minus y squared and the xy orbital. But also feel free to drop in the chat if this is something you've done a million times. So I'm going to give you another literal minute. And the question I'm going to ask you is to help me put these two orbitals on an energy graph relative to each other. Now, the nice thing is, actually, any answer is correct with the right caveat. Okay, it's been a minute. Um, what are we thinking? How do we think about this? So maybe let me clear this. Okay. Let's see if I can draw on the orbitals. Is this helpful? Huh, thanks. Okay, so if we put our coordinate system on the orbitals, now we just want to go back to O2. We always go back to O2. This is what I tell the students in my graduate class all the time. So right here, can you see how this lobe is on the, let's say, x-axis, and it has some overlap with this sigma orbital that's part of our octahedral ligand sphere? This right here is, as drawn, going to comprise, for example, a bonding interaction. And you would have the same interaction over here, same interaction over here, same interaction over here. And then axially, you'll have no interaction because if you have a ball up here, the negative and the positive will balance each other out. Does this make sense? Let's draw a second one. Let's do this one. This is one of the off-axis combinations, so none of these orbitals go through the coordinate system. So can you see how if we have a sigma sphere here, it'll have one bad interaction and one good interaction, and so there'll be no bonding. And the same thing will happen over here and over here and over here. And so with that collection, we'll have no bonding interactions whatsoever. And so this right here in an octahedral ligand field will be a non-bonding orbital. And we can extend that logic to this orbital here and this orbital here. This one's more complicated to see, but we can easily see that in this plane, we'll have a bonding interaction. So we know that no matter what's happening, we'll have some sort of bonding interaction. Is this a little bit more clear? I highly recommend working on this on your own with a pen and paper, as opposed to looking at the horrible whiteboard drawings that I'm trying to execute here. So all we want to think about is, with our crystal field, do we have the potential for some sort of bonding or anti-bonding interaction, or is it a non-bonding interaction because the positive component will cancel out the negative component? And so using this very simple approach, we can actually calculate out molecular orbital diagrams. Now, the trick with transition metals is that because the bonding combination, so with octahedral, these three are non-bonding. So they're all going to be the same energy, and they're not going to bond with the ligand field. The combination that we use is generally the anti-bonding combination. And so it's the sigma, well, it's the something star combination, depending on the nature of it. And so the reason for that is because the d orbitals are interacting with the ligand field over here. The ligand field is generally lower in energy than the d orbitals, and so they form one bonding combination, which is closer in energy to the ligands, and one anti-bonding combination, which is closer in energy to the metals. And so because of that, these are the d orbitals. So I know that that might be a little bit difficult to see if you're not drawing it out with a pen and paper on your own. So let me just ask, would anyone like a minute to try to work through this on their own, or should I move to the next slide? Okay, we're going to move to the next slide. Thanks. This is great. You all are making Zoom as much of an interactive experience as it can without the breakout rooms. Okay, so let's actually look at this. So if we use the crystal field approach, we get schematically what the diagrams will look like. If we go back to the symmetry adapted linear combinations of orbitals, what we're going to get are the orbitals that are actually specifically adapted to bond with these d orbitals. And so you're going to see orbitals that look exactly like the orbitals that can participate in bonding. So what do I mean here? So if these are our symmetry adapted linear combinations, which come from our set of 6 ligands, which we denote L6, we have our metal-based orbitals, and then in the middle of our diagram, we have Ml6, metal with 6 ligands. And so this probably looks like an atomic orbital that we just saw, which is the x squared minus y squared orbital. Can we see this? And this looks like the dz squared orbital in its own way. And so we can take these symmetry adapted linear combinations and we can interact them with other orbitals. Do we expect to have a symmetry adapted linear combination that will match with our non-bonding orbital set? I agree, we do not. This set will match with our p orbitals, which are also metal-based. And then this will match with our s orbital. And so this is our A combination, E, this is also an E, or sorry, T. I wrote it on the wrong one. Okay, this is our E combination, this is a T combination, and this is an A combination for those of you that are having fun with that. Okay, so we can take this and just if anyone is interested on the group theory methodology that gets you the true symmetry adapted linear combinations of orbitals, the way that you would do that is you would begin with the point group. So you would begin with the aggregate of symmetry elements as classified. For example, a fourfold rotation axis and a vertical mirror plane, vertical to the rotation axis of the molecule. And then the point group generates a given set of operations, and each of those operations can show you how different components will behave and interact. And so these are called the characters, these are the orbitals that you get, and then there's some rotational elements. And so if this is something that we certainly don't have the time to go into today. And in fact, when I teach this in um, my graduate chemistry class, it takes us 7 lectures to get to this table. But if figuring out the mathematical way that you would derive a symmetry adapted linear combination of orbitals is something that you're excited about, then look at the book references that David provided, and they'll take you step by step how to get to this table. It won't give you necessarily the intuitive idea of a crystal field splitting, where you just think about whether the orbitals have overlap or don't. But this is a both mathematically rigorous and correct approach to deriving your calcs. So if we want to put everything together, this gives us a molecular orbital diagram. So instead of my scratched out diagrams using the whiteboard, what you can see are how the different metals come together with the different orbitals. And David made this beautiful diagram, which is so much better than the orbitals that I drew. So let's start at the bottom. You can see the fully symmetric SALC, which will of course combine with the s orbital. And this is going to be a core orbital. This is definitely going to be filled. This has so much great bonding interaction that it's going to be super stabilized, right? And then we're going to have the combination of the p orbitals with these other SALCs that looked just like p orbitals. And so then we're going to have 3 of those. Then we'll have the bonding set of these where we have the dz squared and x squared minus y squared, and they interact. And then finally we'll have this core part of, sorry, this core part of the diagram, which David's broken out here, where you have the orbitals in the molecular orbital diagram with the d orbital parentage. Now, the reason these are important is these are the frontier orbitals of the system. This is where your electrons that really dictate the properties of these materials will come to the forefront. So if, for example, we want to create a system that's s equals 1, then we would need to fill in, for example, 1 electron here and 1 electron here, or 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. So you'd have 2 unpaired electrons here. And so in all of these cases, we can design our electronic structure and then we can fill in the electrons. How do we fill in the electrons? What choice do we make to fill in the electrons to the level that we want? Okay, I think we're over an hour into this course, so I feel like less likely to get some answers. So the way that we fill in the electrons is we choose both our metal and our oxidation state, or our charge of the metal. Just by going through the periodic table and choosing how many electrons each metal has, we can design these systems. And this is the way we can design our spin component of the spin optical interface. And so, because there are so many different structures for polarizing these systems, sometimes we might want an S equals 3/2 system. Sometimes we might want an S equals 1/2 system. Sometimes we might want an S equals 1 system. And we design that just by choosing our metal and saying which metal works here. We can also replicate this through calculations. And David made this, and because I see that he's listed some information, this is a hybrid calculation that he, I think, executed to get some computationally derived molecular orbitals for these systems. And what you can see, David chose this molecule really well. He chose it because we have nickel 2 plus, which has 8d electrons, which means that you'll have 2 unpaired electrons in the EG set, which replicates our beginning of starting with our NV center, where you had those 2 unpaired electrons in 2 orbitals of that molecular orbital set. And so the electrons will be in this EG set here. And you can see that this looks exactly like what we drew by hand, right? There's some more radial nodes, which give it kind of a funky look, but you can see that we have an orbital that looks exactly like our DZ squared orbital interacting with the ligand set. The other thing David did really well here is he chose ammonia as a ligand, and ammonia acts as similar to one of these stylized dots that we've been using as possible. Okay, so we can also employ a similar approach to look at other geometries. Now, we can do this with both the crystal field splitting approach, which will give us the correct answer for all of these geometries, and the more rigorous symmetry adapted linear combination of orbital approach. For those of you that are really interested in this, I highly recommend taking each of these configurations that David's brought forward here and practicing the crystal field splitting. David, you can answer the question.
I'm typing an answer.
Okay, I assume because it was by far the easiest for this. But yeah, so we you can see how just your stylized approach to looking at overlap is going to give you pretty much all the information that you would need. So for example, you can see this highly excited DZ squared orbital. So it's been destabilized because there's a very strong interaction axially. Whereas you can also see that you have this XZ and YZ set of orbitals that are effectively non-bonding because there's no possible way for them to interact with anything being off-axis orbitals. This ends up, and in this configuration, because you have the in-plane orbitals that are apart by 120 degrees, you can see that now the x squared minus y squared and xy have become degenerate. And so you can, I think, imagine that this is a really valuable way to create, for example, an S equals 1 system. And so if you said, I want a configuration where the x squared minus y squared and xy orbitals are degenerate, that's a pretty easy thing to do, right? You can just tell the ligands to go into these positions and you get the desired configuration. So this is kind of an answer that you can think about existing here. And if it was something that you wanted to work on deriving these configurations. This is a problem that I think is really fun to work on just to make sure that the idea of metal ligand interactions is intuitive to you. So we figured out a bunch of ways to design the spin states of these systems, right? We tell the d orbitals where to go, we fill in with a metal and electrons, and then we get the spin that we want. The last component that we haven't covered in terms of the spin optical, or in terms of the spin state, is we talked about how with the nitrogen vacancy pair defect and with dioxygen, the degeneracy of those levels is really important because it prevents the pairing of the spins. So we can imagine, and so there's a cost to spin pairing, but there's also a stabilization to going to the lowest energy level. So what causes an electron to spin pair or not spin pair as shown here? And so this is going to be very simply proportional to the splitting in energy between these levels. Is the splitting larger than the spin pairing energy, or is it smaller? It ends up being a little bit more subtle than that, but from a coarse-grained perspective, that's all you need to know. And so the things that lead to that splitting are exactly the same things that contribute to more or less overlap between your atomic orbitals. And so if you're thinking about dihydrogen, if you were trying to make a dihydrogen molecule where your hydrogens were 3 angstroms apart versus 1 angstrom apart, which one would have the greater splitting? So it's the 1 angstrom, right? More overlap, more splitting. And so there are ways that we can have more and less overlap with a transition metal. One of them is the quantity that the electron donates from the ligand to the system. Another relates to the relative energy levels of the ligands, size of the orbitals. So we can think about a lot of different parameters. In general, the rules that we can think about are first row transition metals can be high or low spin. Second and third row transitions are metals are almost always low spin, and um, ligands that are better at some of these forms of overlap give you a bigger splitting. So what does that get you? That gets you both the spin configuration, but you might also think that that's starting to give you the other half of your spin optical interface, which is your optical component. So what dictates your optical emission? I talked quite a bit, I think, about how we want to hit 1550 as a number for emission into fiber optic cables, and we want to be able to control our different emission frequency. If we want to control our emission frequency, we want to be able to think about the character of our starting state and our ending state. And so one thing that we can think about is, for example, emitting from, let's say, a singlet state here. So if our excited state that we're exciting to and then emitting from is a singlet, then we want to be able to control that state. And one way that we can control it is by thinking about the character of this state. We can also think about where it is relative to a triplet state, and we can think about controlling that relative to how big this gap is. And so controlling the gap gives us the identity of the emitting state, and then controlling the nature of this singlet state gives us the frequency that we emit at. And so what we want to think about is to what extent have we stabilized or destabilized this state? And there are a lot of different ways that we can tune that. One way is the overlap between the state and the ligands. And so we've been talking about the molecular orbitals as if they're atomic orbitals, but the quantity of overlap between the atomic orbital and the molecular orbital will dictate a lot of this. So this is another parameter that we can tune to get the right emission. A more complicated way of looking at this is just by tuning the ligand field, we create what's actually a much deeper manifold of states. So we create a collection of allowed transitions. We create a collection of transitions that are forbidden from a triplet state to a singlet state. And then finally, we create 2 photon transitions. And all of those can be used and controlled in different ways in idealized systems. And so thinking about what types of transitions you want access to requires thinking about how strong your ligand field is. So I'll just say that we can bring all of those principles together, and it's possible to make molecules that feature a spin optical interface by tuning all of those parameters. And so we can tune just by the principles that we've learned thus far, the frequency of emission, just by modulating simple parameters about the ligands. And so, in case you're not used to seeing molecular structures, here we have two different molecular structures determined by single crystal X-ray diffraction. Here we have a central atom of chromium in the 4 plus oxidation state, which is D2. It has two d electrons, much like the systems that we've been talking about. They're effectively degenerate in a geometry like this, and these are the d orbitals splitting as calculated, not determined empirically, in a exaggerated, in an extremely exaggerated configuration. And yeah. And we also have carbon atoms are always gray, and we've eliminated the hydrogen atoms for clarity. And so I think these aren't exactly the molecules David's been working on in my lab, but he put similar ones in here. Should have put your, okay. I understand why you didn't. And so these same principles, as we've been talking about, can be extrapolated to other systems, such as a chromium 4 defect in silicon carbide, where that defect, even though it's a defect in the material, is not described in terms, is both traditionally not described and realistically not described in terms of band structure. So silicon carbide is, of course, a material, not a molecule. And when we talk about the properties of silicon carbide, we use a band structure depiction. When we put a defect into that material at a low level, when we have, for example, a magnetically dilute semiconductor, if we're thinking about the defect and its electronic properties, we revert back to more of a molecular depiction. And so this is an example of, I think David took a figure from a paper and modified it, of the electronic structure of, for example, different defects in different phases of silicon carbide. And we can look at how all of these different defects can be described in exactly the same language that we're using for molecules. And when we're thinking about, let's say that we're not molecular chemists, even though I am, we can think about how we would construct a solid state system to have a defect that has the right electronic structure. And in doing that, we would use exactly these same principles. So with that, I think we're going to transition to lanthanides. Yes, we are. Um, okay, perfect. So are there any questions before we transition to lanthanides? Okay. So with lanthanides, we have um, we have some more orbitals. We have our f orbitals. So um, is this, well, I have it written on the slide that's incorrect. What we have here are a collection of f orbitals. Now, the really nice thing about f orbitals, and I'll show this in a couple of slides, is they're so deeply buried within the core that we can actually use the atomic physics that we learned in um, our intro classes, possibly even in general chemistry, to come up with their electronic configurations. Another way to put this is we very much expect the properties of an erbium ion, which is held in place with 6 lasers at nanokelvin temperatures, to be very similar to an erbium molecule at room temperature. And that's pretty unusual that something can traverse, let's say, 11 orders of magnitude and maintain its properties. And the reason for that really is that these F electrons are part of the core. And so when we're thinking about building up lowest energy states using very simple rules from intro chem or physics, however you want to think about it, lanthanides are the perfect playground for this. And this is one reason why molecular-based lanthanide systems have a lot of promise for the quantum internet. So let's say that we want to build up a system. If we're using an atom or an ion as exactly the same in a real molecular system as it would be in theory, we want to just start at the beginning. We want to start with Hund's rules. So the Hund's rules in very simple language, we want to maximize S, we want to maximize L, and then we want to couple antiparallel if the orbital shell is half filled and parallel if the orbital shell is filled. So, ha do you all feel really comfortable with Hund's rules? Okay, thanks. Okay. Um, okay, so for people who are really comfortable with Hund's rules, um, let me ask you one of my favorite questions, which is, tell me what the lanthanide is that has the largest magnetic moment. And for the people who are less comfortable with this, so while the people who are comfortable with it think about that question, I'm just going to break down Hund's rules a little bit further. So when we're thinking about building up atomic term symbols, there are two ways that we can do this fundamentally. One is the way that's usually done, which is called alternately Russell-Saunders coupling or LS coupling. And in this, we take the individual term symbols for each electron and we couple them in the way shown here. So if an electron has an orbital angular momentum quantum number of -1, we add that to another -1, we add up all of them, and we get a capital L. For spin, we do the same thing. Each electron is s equals 1/2, and we aggregate them together, and then we get a capital S. And then we take the capital S, which is the aggregate term, the aggregate, uh, wow, this word has just escaped me, number for a multi-electron atom and couple that with the capital L. We couple those two in a vector-like coupling, just like we couple the individual L's in a vector-like coupling, and then we get our total orbital angular momentum J. Now, the alternate to this, which is effectively never used, is JJ coupling, where we couple a lowercase l and a lowercase s together and get a lowercase j, and then we aggregate our lowercase j's into a capital J. This is effectively saying that the combination of your spin and orbital contributions for your individual electron will couple more strongly together than the electrons will interact with each other. This is sometimes used for uranium atoms, but this is very rarely used and not useful for dealing with simple systems and understanding them. So if we're doing this and we're doing it in a simple system, lanthanides are by far the best playground to understand this. This is the net radial extent of an arbitrary lanthanide and an arbitrary actinide. And what you can see is the 4f electrons are buried within the xenon core. And so this is really unusual to have spins that are buried within the core. And so effectively what that means is they'll interact so poorly with the ligand field or with anything around them that we don't have to worry about modifying them from their atomic number at a first approximation. This does not follow with actinides, where the 4f or the 5f electrons exceed the core electrons. So how do we do this? Does anyone have an answer to the lanthanide that has the highest magnetic moment? So, um, let's go through this. Let's actually figure this out. If we want to figure out the highest magnetic moment of a lanthanide, or of anything that behaves like an atom, we can start here with this diagram where we have the different orbital moments written out for the spins, -3, -2, -1, 0, 1, 2, 3. As you saw with the way that we aggregate our L's and S's, we will be taking the absolute value. So when we're talking about something that behaves like an atom, what will the highest magnetic moment correspond to, S or J? So it's J because we're coupling together both S and L in our atomic system. And so what we want to do is we want to add up our individual electron numbers. So let's say we have a second electron here. We would have 5 for our orbital moment and S equals 1 for our spin moment, right? And then we're in the first half. So how would we couple S and L? Add or subtract? So in the first half, we subtract. So let's say we keep filling. Let's say we get up to 7. If we get up to 7, S is going to be 7 halves, right? L, when we add up 3 and -3, 2 and -2, 1 and -1, and 0, is going to be 0. So J is going to equal S in that narrowly defined case. Now, if we want high J, that means we need to be in the second half of the lanthanide series. And so we want to keep filling electrons. And so let's say we fill the 7 electrons and then we decide to add, let's say 1, 2 more electrons, maybe 3 more electrons. If we want to go past 7 and then we want to keep adding, do we want an electron? How many electrons do we want in the 0 level? Let me see if I can just annotate this out. Okay, I'm going to try this. Okay, so if we have 2 electrons here, what about this? What does this give us? What's the spin here? So I see oops. I see a spin of 2. And I see an orbital contribution of 6 because we're in the second half of the periodic table. I see a J of 8 because in the second half of the periodic table, we're going to add them together. And so that's how we're going to get our highest magnetic moment lanthanide. Now, the lanthanide I've given you is holmium. This ends up being not correct due to a perturbation on the G value of dysprosium. But it is approximately correct, and the same logic gives you holmium and dysprosium as having comparably large magnetic moments. So just by figuring out this configuration, we can design out our spin level structure. And so this can give us ground states that we can manipulate with microwaves or not manipulate with microwaves. The crystal field, which we use as a perturbation, can also dictate some of our optical properties to some extent. But so this is how, by aligning the electrons this way, this is how we get our ground state. Our excited state manifold is effectively going to be how unfavorable a different configuration is. And so what happens if you flip over an electron? What happens if you put an electron in this level instead of this level? In creating all of those states, which aren't the ground state, we create a manifold of other states, and that's what enables our optical properties. Each way that we can arrange this configuration it gives us another state that we can work with. So, is this not advancing? And so if we turn these configurations into an energy manifold that we can use for thinking about emission, the ground state has the largest spin multiplicity, which is what we just said. Two states with the same spin multiplicity can be distinguished by L values. And this is also giving you a sense of what energy scales are dominant here. If the subshell is less than half full, the lowest J corresponds to the lowest energy. If the subshell is greater than half full, the highest J corresponds to the lowest energy. And so with these, we've created effectively a ranking that gives us all of the different energy levels for lanthanides, and this is what enables erbium to emit close to the telecom band, is this relative ranking of energy levels. So I actually think that's all the material that we have prepared for this 2-hour class, which I guess is okay since we don't have breakout rooms. Here are a bunch of references, which include thoughts on molecules for the quantum internet, if you'd like to read more. Oh, and that is it. So I will release you. Is there anything else I have to do?
No, thank you guys so much, David and Dana, for your time. I think, do you have a few more minutes if people have other questions?
Yeah, sure.
Okay,
Yeah,
if
of course.
anybody has questions, you can pop them in the chat. And then as people are leaving, there is a post-course survey. We'd love for you to take a moment to take that. We do heavily rely on your feedback for any improvements and changes that need to be made to the courses.
Aw, thanks. Okay, I think maybe we should let everyone go. Okay, I'm gonna sign off.
Okay,
Thanks,
perfect.
everyone.
We'll close out.